Hello everyone. This session I will discuss principal component analysis. Actually, your second unit is based on the feature selection techniques, right? In the previous session, you studied different feature selection techniques like select k-base method, then select percentile method, right? So one of the technique for dimensionality reduction is the principal component analysis. So actually there are two types of feature selection technique. There are two main categories of the feature selection technique. One is feature elimination technique and then second one is the feature extraction technique. In the previous session, you studied the different feature elimination techniques where directly we remove the features. Those are less important for the machine learning task. We remove all the features, those are less important for machine learning tasks. But in the feature extraction techniques, instead of removing the features directly, we convert the original data with the high dimension into the reduced representation without losing the original information. Right here, point to be noted, student, in the feature extraction technique, for example, in the principal component analysis, we instead of eliminating the features directly, we convert here the original data into the reduced representation without losing the original information. Right. So this session I will cover need of the PCA, then what is PCA and what is the step-by-step process to calculate the principal components, and here PCA with the Python. So actually PCA is a mostly used tool in the exploratory data analysis for making the predictive models. Right. Every time we discuss about the predictive model, actually machine learning techniques are used for predictive models, right? For designing the predictive model, and PCA is the one pre-processing technique, right? Features extraction technique that we use for reducing the dimension into the data set. So definitely, if you reduce the dimension from the data set, right, then the model will be less complex, right? So it is used for reducing the complexity of the model without losing the original information from the data set. So it can be used to reduce the number of dimensions in the data set, find the patterns in the high dimensional data, and visualize the data of the high dimensionality. Right. Then these are some applications of the principal component analysis, right? Actually, this principal component analysis techniques are mostly used in the application where are the large dimensions. These dimensions can be in the thousands, right? So face recognition, image processing, genetic expression analysis, right? So here, why we need PCA here? Right, so you know that the curse of dimensionality, actually here PCA is a high dimension data. You know that high dimension data is extremely complex to process due to inconsistency in the features, which increase the computation time and make the data processing and the data analysis more complex. Many times or every time we say that my machine learning model gives the better result when my data set is very large, my number of dimensions are very large, right? My accuracy of the model will be good or when my data set will be very large. But there is a one pitfall of the high dimension data set, that is curse of dimensionality. So here, for the better understanding, we can discuss one example. Assume you are there is a one line of 100 yard, right? Then your assume you one coin is drop on this line, and you have been told to find this coin. So definitely it will be very easy for you, just by walking on this line, straight line, it will be easy for you to find this coin, right? This is the coin on the one straight line, so it will be easy for you because assume my object is a single dimensional object here, right? My object is a single dimension object. So for in the next image, if you observe my object is a square object here, and assume it is a again a side 100 yards. This square is a sine 100 yards, and again my coin is dropped in this square. So now it will be little bit difficult for you to identify coin here because my object is a two-dimensional object. my object is a two-dimensional object here. So as compared to my straight line, definitely you need to walk through these lines to identify this coin. Right? So my complexity of the model increases little bit here. Right? If you go one step further ahead, right? Now assume my data set is a three-dimensional data. It is a cube. And again, my coin is dropped on one side of this cube. So definitely it will be difficult for you to identify this location of the coin because this cube is a three-dimensional object, right? And you will find here the coin, right? So definitely when my dimensions of the objects, number of dimensions increases, your model becomes the more complex. Right? And that's why there is a need of the principal component analysis to convert this high dimensional data into the reduced representation so that it will reduce the complexity of the model without losing the original information. So here the principal component analysis is a dimensionality reduction techniques that enables you to identify correlations and patterns in the data set so that it can be transformed into a data set significantly low dimensions without loss of any important information. This point is very important, student point to be noted, without loss of any important information. So how it is possible without losing any information? My principal component analysis converts the reduced representation of the data. Unlike your previous feature selection technique, those directly eliminate the features from the data set. Here principal component analysis converts the original data set into the reduced representation. So actually mainly these three tasks is performed by the principal component analysis. First is the remove inconsistencies, then remove the redundant data from the data set, and also remove the highly correlated features. Now why high correlated features we remove from the data set, that we can discuss with one example here. Right? So here the basic idea of the principal component analysis is what? Select the components with the high variance only. Components with the high variance, like this, transform some large number of variables into smaller number of uncorrelated variables called the principal components. So here we remove the highly correlated variables from the data, right? But without removing any feature. Actually, we convert here the original data into the reduced representation with the help of principal component analysis, right? So why here we remove the highly correlated data? Here is one example. Here you can also note down, student, here the basic idea of the principal component analysis is what? Select the features with the high variance. So if you observe here there are two attributes in my data set, age and salary. Age and salary. If you observe, assume my data set contains here, data set is a BICE computer data set, right? So first field is what? My age, and second field is what? My salary. And my class label is what here? BICE computer. My class label will be BICE computer. So my class label will be what? Yes or no, right? So here if you observe, the age value of the customer is lying here between this range only. So if we start my age from here 10, 11, 12, 30, I assume these ranges are from 30 to 31, 32 and 30. Right? So my all the customers here having only the range of age what? From 30, 31 and 32. Assume here. But if you observe here, the variance in the salary field is very high as compared to the age field here, right? If you observe, if you start salary from 10,000 here, if you start salary from 10,000, so here my next salary is 20K, right? Then my here the last customer is of 1 lakh, for example. My salary will ending with here the 1 lakh. So there is a variety of data in the salary field because it is starting from 20,000, 30,000. Some customers are there. These customers are having salary 30,000. Then these customers are having a salary 40,000, 50,000. Then here 60, 70, 80, 90, and then 1 lakh. So if you observe, all these are the customers here, right? And these are only having the age between 30 to 32. So if you observe student here, age is having very less variance. Variance means what? In the variance formula, we calculate the distance of the data point from its mean. So if you calculate the mean of age, it will be 31, right? And if you calculate the distance of every customer's age from its mean value, it will be 1 or 0, 1 or 0. Right? So here variance is very less as compared to this salary. But here, if you calculate the mean of this salary, you will get near about 50,000, right? And the distance between this 50,000 and all the customers will be definitely the high value. So here, my salary is providing more information because variance is high. There is a variety of customers. Those are having the variety of salary here. So for example, if you take this data set here, so with this example, if you see my some of the customers are there. Some of the customers are there. For example, here, so one first customer is there with the age 31, and my decision of means class level is what? Yes. Second customer is again having the age 31, but class level is no. Third customer is having here age 30, but class level is S. With the 32, again class level is yes. With age 31, 32, my class level is no. Means here my age is not contributing to decide the class level here, means to identifying the class level. Because some of the customers are there whose age is between 30 to 32, and my class level is Y. And also there are some customer with the same range with the class level no. So there is no condition of age for predicting the class, that is yes or no. But salary is having variety of data. So here some of the, if you observe, if our data set is having low salary, right? And medium salary. Now, instead of representing the numerical value, I am here putting the categories just for your understanding, right? So some of the customers are there with the low salary. Those have not purchased the computer, right? But the customer with the medium and high salary have purchased the computer, because you can here say that because there is a variety of values of the salary. Those are saying the class level of the class level of the data set, either yes or no. So my salary is more contributing for predicting the class of the new table, right, for the machine learning task. And that's why here there is no use to have the age attribute in my data set. So can we remove age from the data set? Yes, because age is not contributing in the classifying the data. So we can remove this age. So in the feature selection technique, that is select k-base, then select percentile, you can directly remove age from the data set. But principal component analysis, basic idea is different here. Actually, we convert here the original data set into the principal components, right? And we select only the component, those are having the highest variance. And we multiply these principal component matrix with the highest variance with the original data. And original data will have age attribute, but when we multiply this original data matrix with the principal, only selected principal component matrix, right, that multiplication will give you the reduced representation of the data. This is the basic idea behind the principal component analysis. So if you see the mathematical model for the principal component analysis, so it is based on the linear algebra approach, right? And here we need to calculate the covariance matrix for all the features in the data set, which represent the correlation between the all the features in the data set. Then also we need to calculate here the eigenvalues and eigenvectors, which helps to find the principal components, right? Eigenvalues refers to the total variance explained by the each variable, right? As we say that we select the features those are having only the high variance, right? So these eigenvalues and eigenvectors only help you to find the total variance between these features, right? And that's why we need to calculate here eigenvalues, and also we need to calculate standard deviation, which measure the variability of the data, right? Okay, student. So another one example of the variance I want to discuss here. If my two features are giving the high variance, right? When two features are highly correlated, then we remove these features from the data set. For example, here date of birth and age. If there are two features in my data set, date of birth and age, and if you calculate the correlation between these two features, because both the features are providing the same information, right? And their correlation will be 0, and means they both will be exactly correlated, and that we will remove from the one of the feature we will remove from the data set. So either we will keep age or date of birth, right? Because both are providing the same information. So like this, your principal component analysis also uses this concept to reduce the duplicate data from the data set, right? So I hope student you are clear with this. So this is the formula for variance that we discuss. If there is a single, this mathematical terms should be clear to understand the principal component analysis here. So if there is a single dimension data, here my dimension is temperature. How you calculate the variance between this data set? So here is the formula. Here we calculate the distance of every point from its mean value, right? So here X bar represents what? The mean. X bar represents here the mean, and Xi represents my data points, right? So why we take square here? Because the distance never be negative, right? And we find this distance for all the points in the data set for I equal to 1 to n. Here n is nothing but the number of data points in the data set. And we take what? This average of these values, and that's why divider factor is n minus 1. When my data set contains the sample points, we take n minus 1. If you take the population, complete population, then we take the n as a divider factor here, right? So this is the formula for your variance. Actually, variance is the square of the standard deviation, or standard deviation is the square root of the variance, right? So these are the two alternative terms, right? Either we can use variance or standard deviation to find the dispersion of the data, right? To find the distance between the data point from its mean value, right? So this is one of the technique we are using in these mathematics of principal component analysis. See, if my data set is of the two-dimension data set, right? So assume there are two dimension X and Y, temperature and humidity. Then instead of calculating variance, we calculate the covariance here, right? So covariance is the measures the correlation between the variables X and Y. So if this covariance between X and Y is 0, means both are independent variable. If covariance between X and Y is greater than 0, both are in the same direction. Means what? There is a positive correlation between X and Y variable. Means what? They are directly proportional to X is directly proportional to the Y. Whenever X will increase, Y will also increase, right? And when this covariance between these two variable X and Y is negative, means less than 0, both are in the opposite direction, means what? There is a negative relationship between X and Y variable. In other words, X is inversely proportional to the Y. Whenever X will increase, Y will decrease, right? So these are the three possible relation exist between the two dimensions in the data set, right? That we need to calculate for identifying the principal component analysis. So how you calculate this covariance? If you observe, this formula is similar to the variance, right? In the variance formula, we have taken square here. So square means what? xi minus x mean into xi minus x mean, means instead of writing these two terms, you are taking square, because my data is single dimensional here, right? So twice terms are there, xi minus x mean, xi minus into xi minus x mean. So instead of writing two terms, we are taking square here. So here now my we want to find out the correlation between the covariance between the x and y. So there are two terms, xi minus x mean and yi minus y mean, right? And then we find the summation of all these differences of the data points from its mean, and we take its average, right, by dividing n minus 1, right? So I hope student you are clear with the covariance matrix of 2 dimension. So if there is a matrix of more than 2 attributes, right? So how you calculate the this covariance? So here we calculate the covariance matrix for the attributes more than 2 variable, right? So your covariance matrix is this. For example, if there are 3 dimensions in my data set x, y, z, so you will get here 3 by 3 matrix. So if there these rows represent what here, x, y, z. Similarly here in the column x, y, z and row x, y, z. So in each and every cell of this covariance matrix will represent what, the covariance between these two variables, x, x, then y, x, then z, x, then covariance between x, y, then y, y, then y, z, right? So here actually it is only the triangular matrix, right? You need to calculate only triangular matrix, right? So once you calculate this covariance matrix from the data set, with the for this covariance matrix you can identify the eigenvalues and eigenvectors. So I will assume you know the mathematics behind calculating this eigenvalues and eigenmatrix. In short, I will cover here. Here we solve the characteristic equation x equal to lambda x, where this lambda is represent the eigenvalues of the matrix A. So how we calculate this, right? Here we calculate the determinant of A minus lambda I, right? Of the polynomial degree n. Then we find the roots of this characteristic equation, and these roots actually represent the eigenvalues. And once you calculate these eigenvalues, then from these eigenvalues, this each and every lambda, that is eigenvalue, will help you to obtain the eigenvectors of x. Right, so this is the basic mathematics behind the principal component analysis. Then step by step process, right, we will discuss in the next session. Thank you.